the important things that we learned last time. So guys, this has absolutely nothing to do with the homework questions, although it has everything to do with the homework questions. So guys, these are the important bits that we learned last time. So first of all, reaction rates are simply a measure of how fast a reaction is going. So we talked initially about the idea that our unit per time is moles. And that got us thinking about this idea that reactants are turning into products. The amount, concentration really, but the amount of reactant is going down, the amount of product is going up. And then we talked about the idea that amount, or moles, is a horrible unit to use because you can't measure it without interrupting the reaction. So then we switched to molarity, which made even more sense because one, you can measure it without interfering, and two, concentration. Not moles, but concentration is one of the things that affects reaction rate. And then guys, from there we said this: all reactions are slowing down. And we agreed on the idea that the reason reactions are slowing down is they're consuming themselves. As the amount of reactant goes down, there's less reactant to react. Michael picked up on the idea that that's a half-life situation, which it absolutely is, although it's a little more complicated. We talked about the idea that you're going to have to be able to identify these graphically on the test. By the way, guys, just so you know, it doesn't matter what year. I ordered these for you. They're on the way. It'll be the 23. I have literally every year of these going back to time and all eternity. But guys, I'm going to give these to you when they arrive. And so what we're going to do, I don't know if I can immediately find it. Oh, there it was. Yeah, so guys, these are the graphs that we got to be able to talk about. They're in the review. So we're just going to do that as we're reviewing because it's really just memorizing. All right, so we did that. And then guys, the last thing we did is we talked about the idea that the relationships in rates, the relationship at which reactants go down, products goes up, is not always simply one in, one out. And when it's not one in, one out, we need to be able to relate their rates, and we do that through rate expressions. But remember guys, the reactants are being consumed and the products are being made. So to make these equal, we flip the reactants over by making them negative, which just flips it over. And then guys, we divide by the coefficients to account for the fact that it's not one in, one out. It could be two in, three out, and we have to account for that as well. So guys, there's your review in a nutshell. What do y'all want to talk about? Yeah.
So on question 14.4,
yeah.
On part B, it says the reaction is complete, but I thought last time in class we were talking about how the reaction isn't actually complete.
Yeah. No, I'm glad that you brought that up, Jonah. So what we've got is we've got theory and practice, right? So in practice, reactions stop. Because fundamentally what happens, and we're going to quantify this, as concentration goes down, rate goes down, right? And eventually you get to the point where your concentration is so low, it's so diffuse, that while there is reactant technically there, it's so spread out that collisions, right? They collide so infrequently that the rate is functionally zero. So the way that we talk about this is concentration never goes to zero. That's asymptotic. You're always going to have a little bit left. But with that said, rate, for all intents and purposes, does fall to zero because eventually your concentration is so diffuse, they just don't see each other.
Okay.
Is that okay?
Yeah.
Great question. Guys, what else? Done? I like done. Are you really done? Yeah. Uh-huh. Yeah.
So when you set it up,
Uh-huh.
there's two different products.
Yes.
Is that why they separate the two?
Keep going.
It's like
You're doing great. Yeah.
Here, I'll ask you a question on that. I kind of just figured it out
Yeah.
in my mind.
Yeah.
Must be the same.
Yeah.
Like, write it all out.
Yeah, so let me table that because do you have a 25er as well? Why don't you throw them all out and then maybe we can, because your question has bigger implications. Lindsay, go ahead.
I'm just wondering what it's asking when it says, like, what is the rate of total pressure in the
Now, is that in 25? I assume that's B.
Yeah.
Is that B? Okay, so let's talk about that too. And then Garrett, where were you going?
Okay.
Oh, that's what I was talking about.
So-
No, you can't talk about two things. You have to talk about one at a time. Go ahead.
So electron A, where it has 2 moles of hydrogen plus 1 mole of O2 is 2 moles of water.
Correct.
When you're doing the rate expression,
Uh-huh.
do you have to account for the total moles of reactants between the total moles of product?
No. So no, you deal with them as individuals. So hear this whole thought out. When you're writing rate expressions, you will have as many components to that rate expression as you have reactants and products. So if you've got 3 reactants going in and 2 reactants coming out, you're going to have 5. This equals this equals this equals this equals this. With that said, the reality of it is frankly, you really only need 2. Right? Because in these problems, what you're going to have is they're going to give you the rate of something, and then you're going to figure out the rate of the thing they want you to think about. So what I did, and I'm glad you're bringing this up, you don't have to do this on the test. Like, for example, we've got hydrogen and oxygen making water, right? But what it's telling us is it's telling us the rate of consumption of hydrogen, and they want us to figure out the rate of consumption of oxygen. So at the end of the day, this is all you need to write. You don't need to write this and then X it out. I did just to give you exposure to the complete expression, but you don't need to do that. Is that okay?
Yeah.
Hold on, I'm trying to think about questions. You wanted to do pressure. What's that? Did you really? Can you? I'm intrigued because you asked, and I haven't read these questions in a while. It sounded like you asked the question, what happens to total pressure?
I just learned what that meant, and then I read the bottom paragraph, which is telling me what it is.
So is it basically like a Dalton's law of partial pressure thing?
And I just didn't like that.
I totally don't remember that question.
Well, it just asks what, like, the...
Just a second, Elizabeth.
change of the total pressure, so you just have to, like, eyeball the changes in the pressure.
Oh, interesting. Okay, it makes sense to me now. It was funny because I don't ever remember thinking about this question, and I was sort of intrigued by it. But I think it is. So you just find the rate of consumption of and then the rate of production, and then you sort of realize one's going away, one's going up. Okay, yeah, that's interesting. When you asked the question, I was like, oh, that'll be fun. I don't remember that. Okay, so. John, I still want to talk about your question, even though you don't know what your question is. Elizabeth. Yeah. When you say constant, do you mean coefficient? Okay, keep going. What? Yeah, right. So I don't have my writing utensils, but let's do this. And then if this doesn't work well enough, we can go back to my slides from last time, and maybe that'll help. So for example, let's look at 25A, where we've got 2H2 plus O2 yields 2H2O. And so the idea here is that hydrogen will be consumed twice as quickly as the oxygen, right? Because for every oxygen that goes in, 2 hydrogens have got to go in, so that's being gobbled up twice as fast. Then water is being produced at the same rate as hydrogen is being consumed. Hey, Don.
I didn't want to interrupt you. I was just
No.
going to if you had it today, when did you cry?
4th.
Okay. Would you have a minute?
Oh, yeah. Yeah. Oh, yeah.
Okay,
Yeah.
it's my creative writing class that they're going to be.
Would you text me? Because I'll totally forget, but I'd love to come down.
Creative writing is just doing composition.
Yeah.
On the fourth day, so it's going
Yeah.
to be quiet in there. And
Yep, I'd love it. That'd be great. I will forget though, text me. Yeah, okay. And so you guys know that trick, right? If you know that you need to connect with somebody, always put it on them to reach out to you, and then you don't look bad if you forget.
I will forget.
Yeah, oh yeah, yeah. And so back to the thought then, Elizabeth, the rate at which water is being produced is the same as the rate that this is being consumed and twice the rate that this is being consumed, okay? So this then is the idea. When we write equal signs in the middle of these expressions, we literally need them to be equal. So if this is going away twice as fast, so this is twice as fast. If this is going away twice as fast and we want its rate to be equal to this, we've got to divide that by 2. So if this is going away by 10 molarity per second, this would be going away, just making up numbers, by 5 molarity per second. To make these equal, we've got to divide that by 2. That's why we're dividing by the coefficients, because we're trying to make them equal. Do you buy that? Is that okay? Yeah.
So,
Yeah, no, I'm glad, this is why we do this, right? We're clarifying, yeah.
so on part B with that line, because it's gases in
Yeah.
together, how like as you have less particles,
Yeah.
the pressure goes down.
Yeah.
If they were liquids, it wouldn't do, right? Or would it?
When you say liquids, do you mean solutions or do you mean liquids?
If solutions, like if you had the NO2 and the CO2, the 2NO and CO2, if they came together to form a liquid, if they were both liquids and form a liquid,
That's a physical change. So that's a whole different
so
deal.
If they started out as liquids and formed a solution, instead of being 2 gases that form
Again, if you have, it's important that we nitpick this because if you have 2 liquids that come together to form a solution, they're not reacting, they're dissolving.
oh, well then they're just forming another liquid, not a solution.
So if 2 liquids are forming another liquid, you're not going to like my answer. You ready? You can't write rate expressions for that because liquids don't have concentrations.
Why not?
Yeah. So, for example, we're gonna talk more about this later. But the idea is this. This is alcohol.
Yeah.
This isn't alcohol dissolved in water. This is alcohol. And as a result, it doesn't have a concentration. Concentration, by definition, is something dissolved in something else. It's like a density, right? And liquids and solids as well, you're going to find out. Liquids and solids do not have concentrations. Therefore, you can't write rate expressions for them. Yeah, because solutions have densities, and therefore so what can you write rate expressions for? And the answer is 1, solutions, because it's moles per liter, right? The other thing that we can write rate expressions for is gases and mixtures, because remember the idea, Pivnert says that the pressure is analogous with number of moles, right? But then that is going to be number of moles in a vessel. And if we know the number of moles and if we know the size of the vessel, we can figure out a molarity for a gas. It literally is a concentration. So moles trends with pressure. If we know the size of the container, that really is a concentration. But with liquids and solids, they don't have concentrations. You're going to find out in the next unit, we call these things heterogeneous equilibria. And if you have an equilibria that contains liquids or solids, they don't show up in the expressions because they don't have molarities and they don't have concentrations. Yeah. John, can we now answer the question that you didn't think you asked? This is what I heard you say. I heard you say, on 25, I just figured it out. Is that right?
Kind of, yeah.
Let's let that be your question. Okay. So, guys, on number 25, but this is a general principle for everything you do in AP. Many, many times, especially in this unit, even today, hadn't even thought about that. Guys, even today, you are going to be put in places where you can derive the answers to questions either mathematically or logically. And I don't know if that's where you were going, but that's where I went. And so the question is, how do you know whether to do something mathematically? And how do you know when to do something based on logic? And guys, the answer is pick the one that's faster and less likely for you to make mistakes. And you're going to see an example of that today when we start writing rate laws. Guys, determining rate laws, you can do mathematically, but I'm not going to teach it to you that way because there's lots of chances to make mistakes. You good? Okay. We're still grading homework. John, the answer then becomes you pick, because you're right. You could look at, you could look at this in the context of the question, and you could say, what are we looking at? Oh, you could say hydrogen is being consumed at twice the rate of oxygen. Therefore, if hydrogen is being consumed at 0.48, then oxygen will be consumed at 0.24. You could do that in sentence form, and that's fine. Or you could do the math. You got to do one or the other. But again, you're going to pick the path of fast and pick the path of less likely to screw you up. Yeah, so good question. It depends on the question. I don't have my book open. If you read 25A, does it say what is the rate or what is the rate of disappearance? There you go. Because it says rate of consumption, you don't have to put the negative there because it's understood to be consumed. So the question implies the sign. So if you didn't put negative there, you would be okay. But if you did, it's okay too. If it had just said, what is the rate of molarity change for O2, you would have to say negative. Do you understand why? So if direction is not assumed in the question, you have to specifically indicate it. If direction is consumed, like consumption, or is implied, like using the word consumption, then you don't have to. Yeah, go ahead.
On 25B,
Yeah.
and the CO2, that one's really calculations not positive, but in this case, the direction would matter, and it should be negative.
Oh, did I screw that up?
Well, I was just wondering.
No. So that could totally be my mistake. So are you saying we need a negative sign here?
Yeah.
Perfect. Thank you.
But is, like, mathematically, does that still...
Oh, how does that work, you're saying? Oh, wait.
If it become a double negative, then like mathematically right now the negative would cancel. Yeah, it's negative. It is like x is
Yeah. So that's going away. Oh, you know what, Clara? That's interesting.
Would the 56 for as a negative then be the negative and then you do negative.
I don't think so, because the rate that they give you is scalar and not vector. It simply says it says 56 torr per minute.
Because it's decreasing.
Yeah, but I still don't. I believe that the answer is on the other side of the equation. It's in the way you represent your x. Yeah.
reasons why it does point as a negative.
Right. Right. Let me toy with that. That's really interesting. I know that it has to do with the way we assign direction in the original setup, but I don't have a solid answer for you right now. Can we take that one under advisement? At the end of the day, we're smart enough to say, oh, it's going down. But I want to dig into that. That's a really fascinating question. And I don't have a really good answer. Yeah. Linz, did you have?
I'm wondering what on the subject matter why the
Yeah, and that's interesting too, right? Because this shouldn't be negative. And again, it's the opposite example of why this doesn't work out. Let me play with that. Yeah, I mean, we understand direction and we're okay. I want to fiddle with the math on that. There are rules about when you define variables without direction. And I know that's what's messing this up. I'm just not immediately able to explain it. Let me ponder it and can we come back to it? Okay, you guys good? All right. Oh, sure, come in late and then mess things up. We already talked about it. No, I'm just kidding. Go ahead.
I just think my brain is just like I got similarity, but my brain's like that. If you divide by 60, and multiply by 60, what is it? Okay. Yeah. Oh, it's not. That's fine.
No, I said I was so whenever I saw the cure and
When that's
You guys okay? All right. All right, guys, here we go. Let's get this in the book. Boom, boom. You guys are going to remind me to stop recording.
Stop
Thank-
recording, stupid.
That was
Told us to say it.
boy. I'm feeling a little microaggressed. So, there we go. So guys, last time in class, we learned to write what are called rate expressions. And I mentioned in passing that there were these other things called rate laws that you needed to learn how to write. And guys, we're going to do that today. Here's the problem. We're going to be writing rate laws for this entire unit. And guys, many times you forget that rate expressions even exist until you see the questions on the test. And then the very first question, because it's easy, says write the rate expression for this reaction, and you just knee-jerk write the rate law because you forgot about rate expressions, because the only time we're going to do these is last time, and we're not going to see them again until the test. So these are rate laws and not rate expressions, and they're completely different and much more important. So with that idea, guys, let's dig into rate laws and let's get started with all of this. So guys, what? No, you don't need these. No. I only printed the last page.
so we should still take it.
Yeah. Some of you guys told me you don't even like it when I give you notes. That was actually just Lindsay and Claire, but we're going to blame them.
You can never I don't mind it.
Okay, so guys, are you familiar with the term learned helplessness? Are you familiar with the idea that it actually goes by another name? We call it high school. Because guys, in your little high school worlds, teachers have convinced themselves that the best thing they could possibly do is everything for you. As a result, when you actually have to do something, wait for it, for yourself, you don't. Because if you wait long enough, somebody will make it okay, right? And you guys understand this is really tongue-in-cheek because you aren't these people. But guys, we're describing our education system. Seriously. The stuff that I used to be able to get my general chem kids to do was the AP curriculum. It's crazy. So with all of that said, if you're sitting there going, I wish Knappenberger would print the notes for me, they're on our stinking website. Stupid.
I'm feeling microaggressed.
Have you said, or this is in the recording?
Oh, yeah. It's in there. All right, so guys, can we all agree with these ideas? So we've looked back at data that represents the relationship between not moles, amount, but concentration and time. And so guys, it looked like this. This was actually hot out of your notes last time. And guys, we were looking at this relationship as butyl chloride turns into butanol, and we've got time progressing in what are actually not even units, again, because these things slow down. The rate at which they're slowing down is slowing down. So we're tracking molarity. Molarity is going down. As molarity goes down, the rate goes down. And so we can do what are called average rates, which is the change in molarity divided by the change in time. And that then gives us the average rate at any given time. Is that all sounding familiar? Just one second. And we notice that not only is the rate slowing down, but the rate at which the rate is slowing down is slowing down. And we talked about the idea that that is the first derivative, but you don't need to know that. Go ahead. And also, I think it was Elizabeth that mentioned very insightfully, the other thing that we can do is if it's an acid-base reaction, track pH. Is that okay? Yeah? Okay. So, guys, one other thing to mention to you, because I know that some of you are mathematically minded. Do you guys, and forgive, if you don't understand the calculus of this, just tune out for a minute. But guys, you understand that the idea behind derivatives is that you're taking an ever smaller slice of a curve until you get to the point where you have an instantaneous set of data, right? In the case of this sort of math, guys, if you take the derivative of the function that describes the curve of time versus molarity, molarity divided by time, that would be rate, molarity divided by time. If you take the derivative of that, what that allows you to do is find the instantaneous rate. For those of you that aren't doing calculus, never mind, you won't see this here on the test. But guys, this allows us to find average rates. How much is the concentration changing? How much is time changing? Change in concentration divided by change in time is average rate. Understand that when you get into college, you'll actually be doing the derivatives of these functions, and then you're able to find instantaneous changes, which is really the slope at any given moment. So if you understand the math of that, great. If you don't, just understand it's coming. So with that said, guys, here's what we know. We've used this data to come up with average rates. You guys good? Okay, so guys, drink this in one more time. So we've got time, we've got concentration, and from that we're calculating rate. Is that okay? Okay. So guys, with that said, we're now ready to move on. And guys, as we move on, let's consider another reaction, which is this. Ammonium reacting with nitrite to form nitrogen and water. And guys, it doesn't matter what the reaction is. This is the data. Now guys, here's the problem. To your eye, because this is how people learn, you learn through a process called scaffolding and schema theory. This is why your good teachers start every day by reviewing. This is why this good teacher starts every day by grading homework. Because guys, what you're doing is you're building what is called schema. And so the idea behind schema theory is that you learn something new by relating it to something that you learned before. Michael's been a great example of that over the last couple days as he was relating pressure collisions with rate collisions and changes in reaction rates with half-life. Good job, Michael. Guys, what you're doing right now is your little schema brains are trying to take this and relate it back to the chart that I showed you 30 seconds ago. And as you do that, you're being deceived. Guys, this data has very, very little to do with the data chart I showed you previously. And guys, so that you know, this is the data that you're going to see in this unit. You will not see data charts like the ones that we looked at a minute ago. This is the data you need to be able to analyze. So guys, talk with the person next to you about, one, what does this data represent? And two, how is it different from the data that you've seen previously? What does it represent and how is it different? It's because you were relying on schema. You were relying on schema. Did you make up your own key?
Yeah, from the makeup ones, I just...
Oh, thank you. You guys okay? So, we have now reached the point in the day where Jonah has used the word stupid like 17 times. But guys, seriously, all of that self-described stupid was actually schema theory at work. Guys, not only do we learn best when we hang new ideas on old ideas, but we are all very, very guilty of the old adage that says if the only tool you have is a hammer, everything starts to look like a nail. Guys, seriously, when we learn things, we try to apply old strategies to new situations, and sometimes it doesn't work. So what are the differences? Well, guys, looking at this data, and Jonah said it very loud and self-condemningly. Guys, this is not data over time. This is not how does the molarity change as the reaction goes on. And a matter of fact, in this one, we're given two molarities. Guys, we are given the molarity of both of the reactants. But guys, you'll notice what we're given is the initial molarity. And then guys, you'll notice off on the right, we are not given an average molarity, or I'm sorry, an average rate. We are given an instantaneous rate. So here's what's going on. We ran this reaction 8 different times. And this is what you're going to do in lab. The first time we ran this reaction, the concentration of ammonium was 0.01 and the concentration of NO2, nitrite was 0.2. You dump them together, measure the rate, dump it down the drain and start over. Then you do it again. In this second trial, the initial concentration of ammonium was 0.02. The initial concentration of nitrite was 0.2. Dump them together, measure the rate, dump it down the drain. You get the idea? And I'm going to go for a minute. And guys, you do this for 8 trials. So now I have a different question for you. I'm trying to figure out how to ask you this without leading the witness. So guys, let's do this. Looking over the patterns and the structures to these 8 trials, what are the controls and what is the relationship between the uncontrolled variable and the reaction rate? Talk about it. What are the controls and what is the relationship? All right. So, guys, what we are about to do, and you don't need a name, but I'm going to give you the name. What you're about to do is you're going to figure out the reaction orders for this reaction. This is going to start out really simple, but guys, don't confuse simple for important. This is the foundation upon which literally the rest of the year is going to be built. You learned it first here. So guys, let's do this. So what do trials 1 through 4 not have in common with 5 through 8? Go ahead. Yeah, the control.
Which one is the control?
Correct. So here,
I was like,
fixed it. And guys, here this is our control. So for now, and guys, this is important. You can figure out reaction orders. John, this was to your question. You can figure out reaction orders mathematically. I'm not going to teach them to you that way because it involves some exponential thinking that I find is way easier to put in words. So, I'm going to teach you how to do this using words. If you'd rather use the math, I'm going to and you'll see it quickly, but I find that the math is more prone to mistake. So, with that said, guys, when we do this in word form, the first thing you want to do is find your control. The control is the one that's not changing. Guys, I'm going to tell you right now, later on, these get evil because you don't have a control. They're both changing. That's bad. But for now, we'll give you a control. So guys, here our control is nitrite. And now we see a pattern in terms of the concentration of ammonium. Between trials 1 and 2, what's happening to concentration? Doubling. Between 2 and 3, what's happening? Doubling. Between 1 and 3, what's happening? Quadrupling. Between, is there a name for that? Between 1 and 4, what's happening? I think it's sextupling, isn't it? All right, but guys, let's do the easy ones. Between 1 and 2, we have kept the concentration of nitrite constant. We've doubled the concentration. What happens to the rate? It doubles. Now, guys, this. Between 2 and 3, we have doubled the concentration. What is happening to the rate? It is doubling. Between 1 and 3, what are we doing to the concentration? We're quadrupling it. And just by eyeballing it, what happens to the rate? Quadruples. Is that okay? Now, maybe I can do this without making too big of a mess. So guys, now let's look at our other set of data. Down here, between trials 1 and 2, what are we doing to concentration? Doubling. What's happening to rate? Doubling. Between, I don't know, let's go 2 and 4. What are we doing to concentration? Doubling. What's happening to the rate? It's doubling. So guys, right now, all of you in your mind are going, duh. If you double the concentration, you double the rate, right? No. Guys, there are some times when you double the concentration and the rate quadruples. There are some times when you double the concentration and the rate octuples. Some of you are noticing the pattern. There are some times when you double the rate and the reaction doesn't change at all. Or I'm sorry, double the concentration and the rate doesn't change at all. So guys, understand right now I'm exposing you to a very simple example of this, but it's way more complicated, and we're going to look at complicated in a minute. For now, we're just getting the idea. Go ahead. It is not, and that's brilliant question. Is it just the stoichiometry? And guys, does that idea that John just talked about, does it paint a mental picture in your head? So if it doesn't, let's answer your question like this. So this is a 1 and this is a 1, so this is a 1 and this is a 1, and that would make them proportional, right? So doesn't that seem like it might be the stoichiometry? And the answer is no. There's actually, and guys, please hear this. This just isn't fluff. This is a big idea. You cannot figure out, and you're going to find out in a minute, these are called rate laws. You cannot figure out the relationship between concentration change and rate change without doing the experiment. You cannot figure out these relationships. They're called reaction orders. You cannot figure out reaction orders from the balanced equation. You can only do it from experimental data. So the question is why? Why doesn't the stoichiometry represent the relationship? And guys, the answer, and this is going to be next time in class, it's actually this. And I just want you to read it before next time. Guys, the reason, and this is important, don't let this float past you. John's important question is, can't we just figure out these relationships from the stoichiometry? The answer is no. How do we do it? We have to get experimental data. Why is that true? And guys, the reason is because what you have up here on the board tells you absolutely nothing about how reactants turn into products. If it was simply ammonium running into nitrite and they stick and turn into products, then yeah, the stoichiometry would work. But that's not what happens. There can be all sorts of stuff going on in the background, and the rate of the reaction is actually based on what's going on in the background. And the only way we can study what's going on in the background is by doing the experiment. So guys, this is a big idea. You can't figure out reaction orders from balanced equations. You have to get experimental data. That's what this is. On the test, they're going to give you the experimental data. You got to have experimental data. So there were other questions. I think, Kale, you had. Are you sure? Could you ask just because I'm curious?
Well, the reaction could never go down in speed, right? No matter what. If you were to double the concentration.
Oh, yeah, okay, let's talk. I like that. So would it be possible for us to increase the concentration and the reactions slow down? And the answer is for us, no. In reality, yes. And so, have you done AP Bio? Okay, so maybe you have heard of enzymes. Maybe. So let me just say, and guys, regardless of your bio, do you understand Kale's question? Can increasing the concentration of something slow down the reaction? And the answer biologically is yes. There are a lot of reactions in our body right now that aren't happening. A great example of it is forming scabs. When you cut yourself, you want that to scab. But when your blood flows through your arteries, you kind of don't want that to form a scab, right? And so it's called the blood clotting cascade. And the blood clotting cascade is actually normally turned off because of a high concentration of something. And when that concentration goes down, it actually speeds up the clotting cascade and causes your blood to clot. So in the chemistry that we're going to confront, no. But biologically, absolutely. Yeah, for sure. Guys, anything else relative to this? Yeah.
Is the rule of not being able to determine the stoichiometry stuff, does that only apply to the initial rate, or does it all after the reaction rate?
That's a good question, and it's the whole thing. Yeah, it's the whole thing. And again, the reason is because this doesn't tell us anything about what's going on behind the scenes. So can we foreshadow for a minute? It turns out that it's actually these relationships that allow us to peek over the horizon and figure out what's going on behind the scenes. Because if we can establish the relationships between concentration change and rate change, it allows us to go, oh, if that's the case, then maybe this is what's really happening. And those things are called reaction mechanisms, and that's what we're going to get into next time. Yeah. You guys okay? All right. So guys, with that said, let's move forward and so we've been through a big process. Guys, you just learned without even knowing it to figure out what are called reaction orders. And then what you're going to find out is that reaction orders lead to rate laws. So guys, don't write this down, and some of it's conversational. But the idea is this. So guys, rate laws, don't write it down. When we talk about rate laws, this is the foundational idea. Here's what we've established. Increasing the concentration, please don't write it down, of this or this affects a proportional change on the rate of the reaction. That was our duh. Double this, double the rate, double this, double the rate. It's proportional. Guys, we can represent this mathematically. This is what is called a rate law. Write it down. Guys, this is the rate law for this process. Rate is equal to, are you all done? Can I turn you loose on something else? Is that okay? Or do you need time? Are you sure? Okay. So, guys, just 1 second. I want to, so my calculator is programmed to score these tests. So you just got to go 19, you remember this? 19 enter, and then 26 plus, and then 26A, and that's it. Groovy? Thank you. All right. So guys, this is the rate law for this reaction, and we're going to dig this apart in a minute, but we're going to play with it first. So guys, notice the components. What are in the brackets? The reactants. Okay? So this is, if you will, our left-hand side of the data chart. We've got the molarities of the reactants. Then, guys, the left-hand side of this is actually the right side of the data chart where we add the rate values. But then, guys, we've got this little critter here called K. It is a lowercase italicized K. So let's talk about this. So guys, you don't need to write this down. This entire, don't write it down. But guys, when we say rate law, it's actually an equation. This equation is the rate law. So guys, what rate laws do is they represent the relationship between concentration and the rate of the reaction. That's what these things do. But then, guys, along the way, we got this little cutie snuck in there. If you can't remember this, it's worth writing down. Guys, K is the rate constant. Now, guys, we're going to do this. You caught up with me? All right, so guys, what we're going to do is using the data from our previous table, we are going to figure out K. So let me grab the data. And guys, here we go. Here's what we're going to do. 1, 2, all right, let's do this. Ivan, you're going to use the data from trial 1 to figure out K. Ladies, let's have you do trial 2. Garrett, why don't you, and you don't need to do it together, I'm just assigning you data. So the back row boys, let's just have all 4 of you do trial number 3. Taylor, if you would tackle trial 4, and then if the 3 of you want to do trial 5, and then I'll do trial 7, just for fun. So guys, find the value of K based upon your trial. And guys, remember, this is the rate law. So that's where you're going to start. What? Oh, did I miss you guys? Do 6. Sorry. What? I'll do 8. Yeah. Okay, so guys, you got the rate law? Here we go. So I'm doing 8. All right, so. Oh, she toned off. All right, rate, really?
Can you move over like 2 feet to the left or right? Thank you.
I'll just stay here and I'll catch up in a moment. Although let me at least write down the rate law in case you don't have it. Rate is equal to K times the concentration of NH4 times the concentration. All right, at least let me do that. I'm glad you didn't say get out of the way, stupid, because I would have been offended. By the way, guys, I did remember the thing on the last test that I told you you'd forget. Yep. Hey! And you all got it wrong. What? Oh, yeah, every single one of you.
So we didn't have a mic for my.
Hey, you told us you were going to remind us. Like, you're going to look over it.
Once again, learned helplessness. Good. Now we have a scapegoat. And it's even better when they're not here to defend themselves. All right, guys, so I'm going to do trial number 8. Did you notice, though, this? Guys, this is a lifesaver. You'll notice that they put these rates not in proper scientific notation. They kept the exponent the same, and they allowed the root of the expression to leave the standard form where there's one number to the left of the decimal. That makes it so much easier to compare. All right, so I've got, and no, I'm not going to get out of the way, 43.3 times 10 to the negative 7th. I was thinking about the exponent. Is equal to K times, guys, I'm going to get sloppy with exponent or with sig figs. Oh, guys, I don't have a oh wait, no, I do. This is the best thing ever. My scientific calculator got bootlegged into an iPhone app.
What app is that?
It's called 15. Well, no, it's here. I'll tell you later. If you don't know how to use reverse Polish notation, you won't like it. Yeah, this doesn't work. Okay, so guys, I get little k is equal to 2. I'll just go 68 times 10 to the negative 4th. Ivan, what'd you get?
K equals 1.08 times 10 to the negative.
Did I do it wrong?
I got
2.7? Run your numbers again. 2.7, 2.7, 2.7, 2.7, 2.7, 2.7. Guess what, y'all? It's a constant. It's called, you ready for this? John, don't move. Stay. It'll wait. Guys, don't miss this. Ready? This is the rate constant, but it's actually not constant. The things that change it are temperature, surface area, and catalyst. Do you see how that then comes full circle? Guys, what are the 4 things that affect the rate of a reaction? There's concentration, catalyst, surface area, and temperature also change the rate of the reaction. But those things are represented in the value for K. We'll talk more later. Now guys, with this said, we all got this answer, right? And when you do this work on the AP test, all of you will receive no credit. Units. Guys, for the first time in your life, you are now dealing with a constant that doesn't have constant units. And the units of this number communicate information that when we start to review determines the shape of the graph. So guys, let's track units. So this is molarity per second, and then we've got molarities on the other side. So guys, here's how this goes. This molarity cancels with this molarity, so we killed a molarity. But this molarity remains as a unit. And then guys, the seconds are in the denominator, but when we solve, where do they end up? In the numerator. What? Oh shoot, I'm sorry. No, I'm sorry. It goes the other way, doesn't it? I was like, wait, that's wrong. Sorry, we divide the other way. Fixed it. Oh, it does. We're dividing the other way. They're both in the denominator. Thank you. I was dividing the wrong direction. So guys, what are the units for K? Inverse molarity, inverse seconds. So now you're going, wait a minute. Why is this not always the case? Well, guys, imagine that we have a third reactant. And that third reactant has some molarity. Now what are the units for K? Molarity to the -2, seconds to the -1. So guys, you're going to find out that these units communicate information, and you've got to get them right. No units, no credit. So make sure with this, you're always putting units. Yeah?
So if it was just like one atom or molecule or whatever decomposing into 2 molecules, would it be molarity over seconds?
So you'd have molarity over seconds is equal to K times molarity. No, the units would just be inverse seconds.
Well, if you had, like, I don't know if it does, like H2O decomposing into hydrogen and
Sure, but the products don't show up in rate laws. It's only the reactant. And so the idea is, if great example, so if you only have one reactant, you only have one molarity. Those cancel, and your unit for K would just be in inverse seconds.
okay.
Is that okay?
Yeah.
All right, you guys good? All right. So guys, now we're going to get oh, by the way, this is a constant, which means that we should say this quickly. Once you've established the constant, you can then figure out the rate at any set of concentrations. Huh? All right. So now, guys, we got one more little ditty and we are done. Yay. Although this is interesting. Don't say yay, because this is good stuff. All right. So now, guys, we got to talk about what are called reaction orders. We talked about this idea that if you double the concentration, you double the rate, yada, yada, yada. Well, guys, that is not always the case. So, guys, this is what we can always do. It's up to you if you write it down. Well, actually, you should write it down. Guys, this is actually the general form for rate law in its entirety. It's this. Rate is equal to K times the molarity of reactant 1 raised to the m power times the concentration of reactant 2 raised to the n power. We did. They just happened to be ones. We'll talk. Yep. That's kind of the point. Just a moment. Did you get it written down? I'm waiting. You guys okay? All right, so I want to answer Elizabeth's question more publicly, but I also want to tie this back to something that John said, because this is important. So guys, Elizabeth's question was, why didn't we do this before? But guys, follow the thinking. This is our rate law. And if there is nothing written up here, what are the understood exponents? Ones. So why did we understand these exponents to be ones? And guys, the answer is, shoot. The answer is right here. Guys, when we doubled the concentration, what happened to the rate? When we doubled the concentration, what happened to the rate? It doubled. So if we imagine double is 2 times 2, double. So 2 to what power is 2? 1. We did write the exponents. They just happen to be ones. But guys, this is now back to John's idea, the really important, tricky bit, and it's this. Where do we get, and guys, I don't even know if this is in the notes, it might not be. Guys, where does M and N not come from? The coefficients. The only, and guys, it doesn't matter if you've got 7 PhDs after your name. The only way to figure out M and N is to do the reaction. This has got to come from experimental data. So, guys, with that said, this is what we know. M and N are what are called reaction orders. And guys, these reaction orders represent the relationship between change in concentration and change in rate. But guys, as we said, it's not always, actually often, it's not just double this, double that. So guys, let me offer a suggestion. Don't write this down, but watch. You'll understand it, but if you're writing, you won't be able to think about it. So guys, we have what are called zero-order reactants. That means if you double the concentration, the rate doesn't change. Again, I would encourage, just trust me on this. You'll never reread these notes. Then guys, we have what are called first-order reactants. Guys, watch. Double the concentration, double the rate. That's what we saw in our previous example. But guys, you can also have second order reactants. Put on your math hat. If you have a second order reactant, if you double the concentration, the rate quadruples. Do you see how that makes second order the exponent? The exponent. So double the concentration, 2 squared is 4. What if you tripled the concentration of a second order reactant? The rate of the reaction would go up how many times? 9. Yeah? Guys, we also have third order reactants. In a third order reactant, if you double the concentration, the rate goes up by 8 times. It octuples because 2 raised to 3 is 8. Guys, this is how we identify reaction orders. This is what you need to know. You okay? Did you trust me not to write this down? All right. So guys, with that said then, what we're going to do is we're going to take this and we are going to actually look at another example. Before we do, one other idea. Adding up all the reaction orders gives you what is called the overall reaction order. It's a term you need to know, and I will show you an example in just a minute. So guys, we're going to do one of these, and then we're going to call it a day, and then we're done. And I'll give you that note page. You guys all good? Okay, here we go. Data. Guys, it's hypothetical data, but it's data. Sorry, I shot this with my phone and then just cropped it and imported it. This is actually out of an old AP test. So guys, it says this. We've got 3 trials for this experiment. And we've got concentrations of A and B. Notice they didn't even give us the balanced equation because we don't need it. But then guys, we've got rate relationships. So let's pick this apart together. So guys, looking at trials 1 and 2, and we're going to think through this and then we're going to talk about how to do this well. Looking at trials 1 and 2, what's our control? 1 and 2. Comparing 1 to 2, what's our control? A. You're quiet, it scares me. A. What are we doing to B? Doubling it. What happens to the rate? Nothing. 0 order. Now, looking at trials 2 and 3, what's our control? We don't have one. Probably not a good place to look. So what if we look at trials 1 and 3? What's our control? B. What are we doing to A? And what's happening to rate? Therefore, BA is what order? Second order. So this is going up by doubling. This is going up by quadrupling. So 2 to the 2 is 4. That's second order. So now, guys, how do we say this? Write this down with me. Ready? Comparing, and I'm going to be sloppy to write fast. Comparing trials 1 and 2, where 1 and 2, where concentration A is controlled, doubling concentration, and you can write it like this. Doubling concentration B has no effect on rate. Therefore, B is a 0 order, and you can use RCT for reactant. You got to write this out. You got to start with the trials you're looking at. Then you've got to identify your control. Guys, we're going to bleed 2 minutes into the break. We'll take a full break. And then you've got to identify the order of the reactant. Then your second paragraph goes like this. If you don't mind, I'm going to just start a clean page so I don't write so low on the screen. Then guys, looking at our next set of data. So comparing trials 1 and 3. Absolutely. Comparing trials 1 and 3, where concentration B, thank you, Eleanor, is controlled and concentration A doubles, the rate quadruples, making a second order reactant. You jiving on that? You okay? So now, guys, what we've got to do is we have got to write our rate law. And it goes like this. Rate is equal to K. Then, guys, we've got an A and a B. And here we establish that B is 0 order. And then we've established that A is second order. So A is second order and B is 0 order. But what is any number raised to the 0 power? And it goes away. So this is the rate law for the reaction. What do you think, y'all? Y'all good? I know. I know. Okay, so I'm sorry? Absolutely. So, little foreshadowing. John, you're absolutely right. You have to have B to make the reaction go. But the amount of B that's present doesn't affect the rate of the reaction. And how can that be? And the answer is that there's something happening in the background with A that is happening so slowly that once whatever happened to A finally takes place, it just needs to invite in some B and the reaction's over. So we're going to talk about what is called rate determining steps. And if you have a 0 order reactant, you know that that reactant is not part of the rate determining step because it doesn't change the rate of the reaction. So we're going to play with this after the weekend, and we're going to create an analogy for this by trying to shoot paper balls into the trash can, and you'll see how rate determining steps work, and that's going to be our connection. That when we start to see reactants that don't affect the reaction rate, we know that they're not a part of the rate determining step. And these rate determining steps make up what we call mechanisms. So if we have a mechanism that has a 0 order reactant in it, we know that that mechanism is not possible because it doesn't line up with the experimental data. And that's where we're going with this. And what I just said made no sense. But what I want you guys to do, please, is this. Your homework, I'll show you. But then, guys, I made you probably want holes in this, right? Let's do this. Let me throw the homework up. I'll stop recording. Let's take a break. And then I'll have this for you when you're done. So, bump, 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 bump. Guys, this is the page that I'm not going to have you, I gave you a copy of. And here's the homework. And let's stop recording.